Today we shall start with the next topic, and that is language of chemistry. To understand anything, how important is a language? So what is the role of language to communicate with somebody? Similarly, in chemistry, the language of chemistry becomes very, very essential so that we can understand how to write the reactions, how chemically things go forward. Chemistry is one of the most simplest subject or the simplest sciences, just because an entire large amount of data can be reduced using the language of chemistry. Instead of saying sodium chloride, we can just say NaCl. So big names can be converted into small symbols or formulas, and thus the language of chemistry becomes very interesting and important. So how do we go about to understand the language of chemistry? We will see in this chapter. The first thing to understand the language of chemistry is we should know what are the symbols. So a symbol is an abbreviation, or that is a short form for the name of an element. You must have heard short forms like H for hydrogen, He for helium, and so on. It becomes very interesting if we try to use the symbols and make different words. Like on your screen, you can see I have made 3 words using symbols of element. That is genius, players, and fun. So how did we get a genius? We got a genius when we combined a few elements like germanium, nickel, uranium, and sulfur. So if you play with these elements in such a way that you try to make different words from it, it will help you remember the element and their symbols. So it becomes very interesting. So it is good fun to use the symbols and play and make words with that. So how will you have fun? You can have fun with fluorine, uranium, and nitrogen. That makes it F, U, and N. Now how do we use the symbols? For that, we should first know atomicity. Now, what is atomicity? The number of atoms contained in a molecule is called its atomicity. So, let's look at some examples here. If we are talking of a water molecule, you must have all known about the chemical formula for water, that is H2O. So, we have 2 atoms of hydrogen and 1 atom of oxygen. So, the atomicity of water molecule is 3, that is 2 plus 1, that is equal to 3. So that's the atomicity for water. So same way, if we are just talking of a hydrogen gas. Hydrogen gas is made up of 2 atoms of hydrogen. So the atomicity of hydrogen gas is 2. Next comes formula for elements. Now you have some elements which are monoatomic. That is, naturally they occur as a single atom. It doesn't form bimolecular molecules. So it doesn't form diatomic molecules. So example of monoatomic elements are all the noble gases like helium, neon, argon, krypton, xenon, and radon. So what you can see on your screens, these are all noble gases. These all are monoatomic. Means when you find the atoms of this gas, they are individual atoms, not as a molecule. Now, why we are talking that not as a molecule? Because most of the gases that we have studied, like hydrogen, nitrogen, oxygen, fluorine, chlorine, etc., the elements like bromine and iodine, these are all present in diatomic state. Di meaning 2. So 2 atoms of hydrogen combine to give us 1 hydrogen molecule. Similarly, 2 atoms of nitrogen combine to give us 1 nitrogen molecule. And so on. So these are diatomic elements. We need to keep these gases in mind, because whenever we write chemical equations and you want to say hydrogen is reacting with chlorine, you won't write H plus Cl, but you will be writing it as H2 plus Cl2. Why? Because atomicity of these gases is 2, it's diatomic. So again, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine and iodine. These are all diatomic elements. Now let's see the triatomic elements. Ozone is an example of a triatomic element because the molecule consists of 3 atoms of oxygen. 3 atoms of oxygen. That's why ozone is a triatomic element. We also have phosphorus. Which is made up of 4 atoms. So it is written as a P4 molecule. Phosphorus molecule is represented as a P4 molecule. And then we have sulfur, which is made up of 8 molecules, and hence it is called as octaatomic. So 8 molecules meaning octaatomic molecule of sulfur, S8. The next thing we come to is the formula of compounds. Compounds are represented using the symbols. Like if you have seen, carbon is C, oxygen is O, but the formula for carbon dioxide is CO2. The formula for carbon monoxide is CO. And as per the list, we can see that not only the symbol is used, there is some number written in the subscript. There are some numbers written in the subscript below. So why are these numbers written? How and why do we write a particular number? Why is it CO2 and not CO5 or CO7? There is some logic behind this. This will come through from the valency of the individual atoms of carbon and oxygen. So from the individual combining atoms, we will get the numbers what we are to write below. So we need to know the first thing is the valency here. So how do we write these chemical formulas? There is a compound barium phosphate which says barium Ba3, and phosphate is a group, that's a radical. Phosphate, this is a group, okay? So this is the positively charged ion, that is barium ion. It has positive +2 charge, and phosphate has a -3 charge. The charges get exchanged, and with a cross valency we write the names. This we will be seeing in the screens to follow. Similarly, iron 3 sulfate. When we write the name of the compound, we write iron 3 sulfate. This 3 is written in Roman numbers. What does this mean? It means that iron's valency is 3. But then why have we not written it for barium here? We have not written it for barium because barium has only 1 valency and barium's valency is 2. So wherever we come across variable valencies, at that time we need to write the number in capital Roman letters in brackets after the name of the metal. They are mostly metals that have variable valencies, and the variable valency of a metal is written in Roman numbers, in capital Roman numbers in brackets after the name of the metal. So barium phosphate will read as Ba3, PO4, where PO4 is a phosphate group. Phosphate group is made by the combination of phosphorus, that is P is for phosphorus, O is for oxygen. So this is a negative radical, phosphate radical. Okay, the overall charge on a phosphate radical is 3-, and hence with the cross valency, the formula for barium phosphate will work out as Ba3 PO4 twice. We have some more examples of compounds which have different names and which is represented by a chemical formula. So baking soda is also called as sodium hydrogen carbonate or sodium bicarbonate, and its chemical formula is given by NaHCO3. So instead of writing sodium hydrogen carbonate, you just write capital N small a, because Na is 1 element, then H is capital, CO capitals, and the subscript number 3 for oxygen. So instead of writing sodium hydrogen carbonate, there's such a small thing that you need to write NaHCO3. So when we learn to write the names of chemical compounds, the writing comes down, or the writing part reduces to a great extent. And that is the beauty of this chapter. We've got some examples that you can see, the names and chemical names as well as their formula. Now, as I discussed earlier, the formula depends upon the valency. So it is important for us to learn the valency of the first 20 elements. So first of all, if we know the elements in order, that is hydrogen, helium, then comes lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium and calcium. Children, you need to remember these 20 elements in a line, because when you know them in a line, you also know their atomic number, because hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, boron 5, carbon 6, nitrogen 7, and so on. So once you know the elements 1 to 20, it is very easy to place them in this type of a periodic table and know their valencies. So to see the valencies, elements hydrogen, lithium, sodium and potassium. Hydrogen, lithium, sodium, Na is sodium and K is potassium. These elements have valency +1. Okay, their valency is +1. Why the valency is +1? We have already finished structure of atoms. So if you take hydrogen atom has only one electron. So it has a tendency to give or to accept one electron. So hydrogen behaves like a metal. Very often it gives off or it shares its electron. So hydrogen's valency is +1. Why +1? Because if it loses the electron, it will have an overall positive charge because it has lost its negative electron. Same thing with lithium. Lithium has 2 electrons. That makes that in the center it has 2 electrons and in the next orbit it has just 1 electron. So there's a tendency of lithium to lose that 1 electron and then it will have a positive charge. Why? 2 electrons and 3 protons. So excess of protons. So they will have a +1 charge. Similarly, sodium, the atomic number is 11. So 281, it loses 1 electron and hence it has positive charge. So the elements that lose electron are called metals. They have positive valencies. So hydrogen, lithium, sodium, potassium, +1 valency. Beryllium, magnesium and calcium have valency +2. When it comes to boron, boron's valency is 3. Aluminium valency is 3. Carbon and silicon have valency 4. Nitrogen's valency. Now here, when we are talking of nitrogen or phosphorus, they have 5 electrons. They have 5 electrons in their outermost orbit. They have 5 electrons in their outermost orbit. 1, 2, 3, 4, 5. So to complete an octet, they want 3 more electrons. So if they pull 3 more electrons, that is, they will have 3 negative charges extra. So to complete their octet, if they need to complete their octet, they need to pull 3 more electrons. So if they pull 3 more electrons from outside, so they will have a -3 charge on them because 3 negative charges they have taken. Similarly with oxygen, oxygen needs 2 more electrons. Oxygen's atomic number is 8. So with atomic number 8, it has 2 electrons in the first orbit and it has 6 electrons in the next orbit. It has 6 electrons in the next orbit. 1, 2, 3, 4, 5, 6. But to complete its octet, it needs 2 more electrons. So if it pulls 2 more electrons from some other atom or another oxygen atom or shares with them, it will also pull 2 electrons, means 2 negative charges, and hence it will have a negative charge of 2. So the valency of oxygen is 2-. Fluorine and chlorine have 7 electrons in their outermost orbit and hence they have a 1 negative charge. Similarly, because they both are in want of only 1 electron, so it will have a 1 negative charge. So if we talk of the elements here, these have the positive valencies and from 3 to 1. From 3 to 1, they have the minus or negative valency. This is -3, -2 and -1 valency for elements like nitrogen and phosphorus, oxygen, sulfur and fluorine and chlorine respectively. Next, we see chemical formulas. How do we write chemical formulas? As already discussed in the earlier screen, Once you know the valency of a element, we write the valency charges as shown here in this table above. Whenever we are writing an ion, calcium ion, this here that circled is shown as a calcium ion. It shows as a calcium ion. So calcium ion has a +2 charge. Calcium ion has a +2 charge. And sulfate ion has a 2- charge. It has a -2 charge. So 2- charge or -2 charge. The charges get exchanged. This is taken down here. This one is taken down here. But since both are 2, they get reduced. So we don't write it as calcium twice, SO3 twice. This is the cross valency. Calcium twice, SO3 twice becomes a cross valency. And since both the numbers are 2, it is further reduced to write it as calcium sulfate. So no need of the brackets. Sulfide, this is, no need of the bracket here. Calcium sulfite is written as CaSO3. Similarly, as we discussed barium phosphate, let's see ammonium sulfide. The third example here is that of ammonium sulfide. So NH4 twice S. Now the valency of ammonia here is +1 and sulfide's valency is 2-. So how will we write? We will write this as NH4 2 times and sulfide, because ammonia's valency is 1, here 1 comes, but the number 1 is not written. So the formula will come out as NH4 in the bracket 2 times S. NH4 in the bracket 2 times S. So this is how we write chemical formulas. Let us see some more examples to understand this better. Okay, this is an example of ammonium chloride here. So we say what we do, first we write the symbols and then we write their valencies. So your ammonium symbol is NH4, chloride symbol is Cl. So the valencies of ammonium and chloride are +1, -1 respectively. So they are +1, -1 respectively. So NH4, which has a +1 valency, this valency will move to chlorine, and chlorine's valency will move to ammonium, NH4. And since they both are having 1 valency, that 1 is not written. And the formula for NH4Cl is, that is ammonium chloride, is NH4Cl. Let's see one more example. Now calcium oxide. So first we write the symbols. Calcium is Ca, oxide is represented by O. The valencies of calcium and oxygen, they both are 2. Calcium has a +2 valency, oxygen has a 2- valency. So calcium's valency will move to oxygen and oxygen's valency moves to calcium. So we write it as we see in step 4. As we see it in step 4, it is written as Ca2O2. But we reduce this to the lowest ratio possible and we write it as CaO. The lowest ratio possible is Ca1O1, and we don't write the number 1. So it's understood if it is calcium 1 means this calcium Ca is sufficient. So thus we write the chemical formula as CaO. So how does this cross valency work? Let's see a few more examples. Magnesium, as we know, its valency is 2+. Bromine's valency is 1-. So when you cross it, the cross valency is written as, bromine's valency will be taken for magnesium. Magnesium's valency will be brought down to bromine, and the formula is written as MgBr2. So what you need to note, children, when we write the cation or anion formula, that time we are always writing the cation charge or the anion charge as a superscript. So when ions are written, the charges are written as superscript. But when the formula of the compound is written, at that time the numbers that will come will be written as a subscript, that is below the alphabets. You should not write the formula as MgBr2. No, this is not the way to write it. The way we write it is as it is shown here. MgBr2, where 2 is written as a subscript. So the 2 should come as a subscript. You have to write it like this. I hope that this is clear here. Let's go to the next example. That is example of aluminium oxide. Aluminium's valency is 3 and oxygen's valency is 2 minus. So when we write the cross valency, we get Al2O3. So here also we see that the 2 charge from the ion of oxygen, that is from oxide ion, comes down, and it is written for aluminium at its base, and the plus 3 valency of aluminium comes down at the base for oxygen here. The next topic that we have in this chapter is writing chemical equations. What is a chemical equation? It is a representation. It is a representation of a chemical change. So if you want to say that hydrogen reacts with oxygen, maybe the electric current is passed and we get water. So the worded equation can be written as in words. Hydrogen plus oxygen gives us water. The next type of equation that we have here is a skeletal equation. Skeleton equation, or we also call it as skeletal equation. Here hydrogen, now as we discussed in the beginning of this chapter, hydrogen is diatomic. So we will always write it as H2. So H2, oxygen is also diatomic. So we'll write it as O2. So H2 plus O2 gives us water. But this equation is not balanced. If you calculate the number of hydrogen atoms and oxygen atoms on the left hand side of the equation, that is before the arrow, and on the right hand side of the equation, that is after the arrow, it is not balanced. So the portion of equation that is before the arrow, these are called your reactants. These are the reactants. Reactants, why? They are taking part in the reaction. And what you get, what is the product? So that is called the products. Reactants and products. So a skeletal reaction will have the reactants and products and written in its correct atomicity. But they may not be balanced, because here if you calculate, we have oxygen 2 atoms on the reactant side but only 1 on the product side. So to balance this equation, we have to change the coefficient. Coefficient is a number that can be written in front of the atom. So if you write a suitable number in front of the atom and balance the number of atoms on both the sides, then our chemical reaction will get balanced. So in this case, to make oxygen 2 on the right hand side, we'll need to add a 2 here in the first place. So once we add a 2 here, so we are putting a 2 in front of hydrogen. Now what happens? Oxygen is balanced on both the sides, but hydrogen has lost its balance. Hydrogen is 2 on the left hand side and it becomes 2 2s are 4 on the right hand side. Now to balance this equation, we will add 1 2 here. So once you add this 2 here, now you got 2 2s are 4 hydrogens on the left hand side as well as the right hand side, and we have 2 atoms of oxygen on the left hand side as well as the right hand side. So now our equation is balanced. So this is how we balance chemical equations. So what's a skeletal equation? Once again, a skeletal equation are those equations which show the reactants and products so formed without balancing them. It is also called as a unbalanced equation. Skeletal equation is also called as a unbalanced equation. Now balancing chemical equations. So what are the steps in balancing chemical equations? The first thing is we write the reactants and products. Then we find an atom which occurs in only one substance on both the sides. So whichever has lower frequency, lesser occurrences, we will try to take that element and try to balance. So in this equation of C3H8 plus oxygen giving us carbon dioxide and water. Okay, so this is propane and oxygen giving us carbon dioxide and water. So we are trying to balance carbon atoms. So once carbon atoms are balanced, then we go to the next. Then we find the coefficient to balance this atom. So once carbon is balanced in step 3, then we will find another unbalanced atom which occurs in only one substance. So over here we see hydrogen is one which is which is there to be balanced. So we'll try to balance hydrogen after carbon is balanced. So in trying to balance hydrogen, we find the coefficient to balance this equation. So we try to balance hydrogen on both the sides. Now since it is 8 on one side and 4 2s are 8 on the other side, it is balanced. Now we repeat the steps of balancing the remaining coefficient till every atom given in the equation is balanced. So if you see this equation, which are the elements that are there in that? We got carbon, hydrogen, oxygen. So carbon, hydrogen and oxygen, all the 3 elements need to be balanced. So the 7th step is make sure that the coefficients are reduced to the smallest whole number ratio. So suppose the equation that you can see here is in the multiple, that is 2CH3 C3H8 plus 10 O2 plus 6 CO2 plus 8 H2O. So if it is doubled or if it is tripled, so we need to reduce that and bring it to the lowest coefficient possible. So you'll have to take a LCM of all the numbers, and if it is already in the reduced state, like example in this equation, we'll leave it as it is. So in that case the equation gets balanced. So here the balance equation will be CH3 plus 5O2 giving us 3 times CO2 plus 4 H2O. We need not write the number 1 as a coefficient. Just as we do not write 1 for the elements down. So wherever there is an element like H2O has 2 of hydrogen and 1 of oxygen, we don't write 1 for oxygen below. Similarly, if you do not write the coefficient 1 is fine. We do not generally write the coefficient 1. Okay, the next topic is what information do we get from a chemical equation? So chemical equations gives us the number of relative atoms taking part in the reaction and the products and the molecules that participate in the reaction. The coefficient of a balanced chemical equation gives the relative number of molecules or moles. This comes very handy in solving physical chemistry numericals later. So balanced chemical equation which represents a proper chain is required to know how much quantity of which substance is required for the reaction. So let's summarize what we have covered today. We have seen what are symbols, what is atomicity, chemical formula, valency, cross-valency, chemical equation, skeletal equations. We saw how to balance chemical equations and what informations do chemical equations give us. I hope that this chapter is clear to you. Thank you.